I should have done this a little earlier. Okay, we're on. So our next talk upcoming here is Jesse Young and Carl Schuett, and they will be talking about exploiting medical devices and proprietary protocols. Okay, guys, you're on.
Hey everyone, thanks for attending our talk. I have to admit this is a little bit different than what we're used to. I can't picture everyone in the audience naked as a way to calm my nerves. So in fact, I'm just going to stare at this webcam. Hopefully everything. This is our talk on exploitation of medical devices, specifically focused on remotely controlled insulin pumps. I'm Jesse Young. I'm a security researcher with QED Secure Solutions. Prior to that, I worked at Microsoft in Azure and Microsoft Security Response.
Hey, guys, your microphone's cutting in and out a little bit. Yeah, sorry.
Better?
Let's give it a shot.
Okay. My name is Carl Schuett, also a security researcher with QED Secure Solutions. Prior to that, active duty Air Force for 22 years, mostly as a programmer. Yeah, and before we want to get into the actual meat and guts of the talk, we like to just take a moment to recognize lots of the pioneers for information security that have done some pretty impactful research, and specifically the names that are highlighted there. Barnaby Jack, Jay Radcliffe, more recently Billy Rios and Jonathan Butts. They've done a lot of work in the remotely controlled insulin pump space as far as security research is done. So I just want to recognize those folks before we get into it. So this is the device that we're going to take a look at today. It's called the MiniMed 508 insulin pump, manufactured by Medtronic. First manufactured in 1999, but was still widely in use up until recently. In fact, we got the pump right here that we've done our work on. It's a pretty simple device, consists of an infusion pump and remote control for remote access. So how do these insulin pump systems work? Effectively, you have what's called an infusion set. It's got some tubing and a needle that goes into the patient.
Okay.
Actually,
guys,
glucose monitor.
We're still having the same problem with you guys cutting in and out. Would you mind if you pop open Discord real quick, go into user settings, and let's turn your gain up a bit.
Sure.
So under voice and video. That's input volumes turned all the way up. Okay, never mind. Uncheck automatically determine input sensitivity. And let's see if that's a little better. So you might want to turn that level down just a little bit towards the L. Yeah, there you go. Let's try that.
Sure. Okay. All right. Let's do this. Let's try this again. So effectively, we have the insulin infusion set that I was talking about there. In this depiction, there's actually a glucose monitor as well. That glucose monitor basically reports the patient's glucose levels at any given time. This particular infusion set is just the infusion set. There's no monitor there, so it just does medicine delivery effectively. As we stated, the device itself is pretty simple. There's not a whole lot to it. And it does come with a remote control so that you remotely access it. The primary use case for that would be a common use is for the pump to be used with small children. And the parent may want to control the device without the child being able to provide any input so that they can't accidentally start the delivery of medicine or stop the delivery of medicine. The problem is that the communication between the remote control and the infusion pump is over clear text radio protocols. Anyone with a wireless capture device that can operate in the
spectrum that it uses can listen in on those transmissions. In fact, even your garage door remote is probably more secure than what you would see here. At least that uses rolling code so that you can't. It's not susceptible to abuse. The only authentication is actually done by entering in the 6-digit serial number. Hopefully you can see, here's an example on the back of the remote control we're using. You load that serial number into the infusion pump, and the infusion pump will only listen for commands coming from that specific serial number. So that makes the device susceptible to spoofing replays, specifically because you can capture that traffic and then replay it. Or in the case of what we're going to show you today, crafting our own commands and sending arbitrary commands to the device.
Yeah, and actually the public disclosure of the fact that this insulin pump is susceptible to capture replay attacks, that was actually snuck in by these guys back in Black Hat 2018. They were doing research and demoing their vulnerabilities that they found in a pacemaker programmer built by the same manufacturer. And then they snuck in this insulin pump and they said, we just do a capture replay, but we're pretty confident somebody could figure out how to arbitrarily craft and send their own packets without the need of a control. And effectively, that's what we've done, what we're going to talk about today. Some of the things that make this particular insulin pump and remote control combo a prime candidate for exploitation are these factors here. It operates on a frequency of 418 megahertz, so that's within the band of freely available spectrum for the FCC. Also, it operates on what's called on-off keying for data modulation. So that makes it really simple to determine, like, is there data in the air or is there not data in the air? A 1 is essentially presence of signal, and then a 0 is represented by a lack of signal. So that thing makes things pretty easy. There's also a pretty simple encoding mechanism for the data, and Carl will get into that later. And finally, there's only a single channel of data that we have to replicate when we're doing our reverse engineering. We don't have to try to spoof responses from the pump. We just have to figure out how to craft messages. That all makes things a bit simple for us, actually. So we're just going to walk through kind of the methodology of how we approach this thing. Up front, Carl mentioned there's a serial number on the back of the remote. There's also an FCC ID on the back of the remote. So most devices or all devices that communicate wirelessly in the US at least have to have this ID, and you can use that to look up the frequency that the device actually operates on the FCC's website. So that's what we've done up front. Where do we have to focus our tools on? And then as far as tools are concerned, we just have a suite of commodity hardware and software that we use to do the reverse engineering. So we use software like RX tools, Inspector, Universal Radio Hacker, which is a lot of in this presentation. And then as far as hardware goes, we use our laptop, a HackRF1, awesome software-defined radio, and then actually a cheaper software-defined radio called the Yardstick. That enables us to kind of custom craft our commands, and Carl will get into that later. You'll see here, this is kind of our capture process. It's really expertly depicted of how we do software-defined radio work. We have the remote control on the right-hand side, and effectively all we're doing is we're pressing all of those 3 buttons and capturing what those signals look like. We press the button. And we're feeding that into tools like Inspector and Universal Radio Hacker so we can get a deeper look as to what that data looks like.
As Jesse mentioned, we need to look at the actual radio data. So we take our samples, usually in IQ format, and use primarily Universal Radio Hacker as the analysis tool. That was the one that gave us the best results. So what you see here in each of these 4 pulses is a single press. Since there's no two-way communication, there's no negotiation, the transmitter simply repeats the command over and over again, usually until you hear an on the infusion pump. But we need to zoom in a little bit further to see what's actually showing up in this data. So when you zoom in, we kind of start to see what we expect to see in a data transmission. You've got especially in an old VHF, you see your preamble for the receiver. That's usually a regular pulse that's used specifically to wake up the transmitter and tell it that it's about to receive data. That's followed by a sync pulse. The sync pulse has specific timing characteristics. It's used to tell the receiver the timing characteristics of the data that's about to receive and how accurate the transmitter is. And it also marks the start of data. Once the sync pulse is complete, the receiver knows that everything after that is data. And then we see our irregular pulses, obviously the actual contents of the data packet. Yes. Better than before, though. Okay. Hopefully this will do the trick. All right. So here we're zoomed way in on the signal. We can see here that the clear presence of our 418 megahertz carrier wave. We see the obvious on-off, and we see the presence of the Manchester encoding. And Manchester encoding is just a way of transmitting data where there will always be a change in state in the middle of a pulse. And that's done to keep the timing more accurate of the actual signal and to prevent problems with transmitting items like long strings of ones or long strings of zeros where the receiver may lose its timing sync. So the data is actually carried on the transition rather than on the level. So zero, I forget which way it goes, but I think a zero is a low to a high and a one is a high to a low. That transition actually tells you the bit. So each pulse has a width of t, but the data that's on that pulse is actually at the midpoint or t over 2. So you will always have some type of transition in the middle of each pulse, even if the level from one pulse to the next is carried over.
Yeah, so effectively, once we capture that data and be confident that we're getting clean and accurate kind of repeated samples, Universal Radio Hacker actually does this awesome job of taking that data and pumping it into a binary representation, even a hex representation. But if you recall earlier, we were talking about the way that the remote control authenticates to the pump, and that's by means of transmitting its serial number. So in this data, we're effectively looking for the serial number. And once we apply the Manchester 2 encoding that Carl was talking about, we can see the serial number called out in the raw message itself. So now we have the serial number, we can begin to understand what the other pieces of data look like. After lots of message samples, we find that following the serial number is actually the command or the button that's being pressed. So in this example, there's also a message counter that increments with every single button press. And then finally, there's a checksum, right? So at this point, we're pretty confident we're looking at the message in the way the developer intended to view it. But we know what's in it, how it's encoded, what the commands are, but we actually don't know how that last bit of data, the checksum, is built. So effectively, that's the last piece that we have to figure out with the craft our own messages. So luckily, the checksum is just an 8-bit value. We actually use this library a lot. It's called CRC check. We plug into this Python library. We find a CRC algorithm that gets us close to calculating the checksum based on all the samples we have. And we actually come across this instance where we're only 50%. We have either an init value of 0 or an init value of 21 that gives us accurately crafted data each time. But we actually notice that there's a catch, and all of our checksums that we calculate seem to be even. So now we can begin to think, oh, we probably just have some sort of bit parity miscalculation here.
So with that little bit of clue, we kind of went back and took a look at the data that we had. Using that same init value in every instance of 21, we realized that those incorrect checksums that we were getting on values where the data ended in an odd number, if we just subtracted 1 from the checksum value, we actually got the correct checksum value. So as Jesse said, this was likely a bit parity issue. But with that calculation complete, we've now been able to replicate the data coming out of the transmitter with 100% accuracy. So we know what's in the data. We know how that data is supposed to look like. Now we need to transmit our own crafted messages. And we're going to talk about the tools to do that on the hardware side, but on the software side, we need something that can interact with software-defined radio. And the Yardstick works with an awesome library called RFCat. It supports Manchester encoding, but we need a little bit more flexibility specifically with individual data because it placed some rules on how it was encoding the data. So we rolled our own Manchester encoding scheme. As we were talking about earlier, the data is carried on the transition, so we just change each bit of our data into 2 bits of encoded data. The 0 is a transition from a low to a high, or 0 to a 1, and a 1 is a transition from a high to a low, or a 1 to a 0. So now our data is encoded. All we need to do is transmit it. So the tool for that was the Yardstick 1 that we've mentioned multiple times. It's got a number of characteristics that are helpful for us, and that we need. It supports the data rate that we were looking for, which through measuring it in Spectrum or Universal Radio Hacker, we determined was around 40,070 bits per second. But the receiver is flexible enough that you can deviate from that and it'll still function. And it does on-off keying. So now we need to see if the data that we're transmitting, that we're crafting ourselves, actually looks like the data that the remote control produces. So on the top is the data coming out of our Yardstick using our software. On the bottom is the button press. We're not getting the same repetition rate, but it's close, and the receiver still recognizes the data. But more importantly, Universal Radio Hacker decoded the contents of the individual packets to be exactly the same between both. So we're confident at this point that we've accurately replicated the transmitter. Zooming in, we see that maybe we don't have the same performance with the reduction of noise from the transmitter turning on to off. But again, the receiver had loose enough tolerances that didn't matter. And again, the data looks the same. And even further, we see our carrier wave. We see the same data. We think we've got the solution. Now all that's left to do is wrap our software into a nice Python package with a front end and pretend to be a remote control for a MiniMed 508 pump. So with that, we're going to move over to a quick demo video.
Yeah, hopefully this stream's fine. We're in the rehearsal. So this is essentially a really sped up version. We're setting up the pump right now to listen for a remote control that theoretically doesn't exist. We're going to give it a serial number of 0, 1, 2, 3, 4, 5. And you see there is actually just turn RF mode on. So I made it to where the pump will listen for remote commands. You can see I'm putting in 0, 1, 2, 3, 4, 5 as the remote control to listen for. And we're going to program that all in our software. We're not going to use the remote control at all to make this thing deliver insulin. One other setting I just put on was called child block. And that makes it to where you can't press the buttons on the pump itself in order to stop insulin from being delivered or to start insulin being delivered. So right there we just sent an activate command. We're bumping up the medicine levels purely on our software. And we're sending another activate to make it recognize and acknowledge, hey, I'm going to start delivering insulin right now. And this is a really, really slow process. The delivery of 8 units of insulin from this pump takes maybe about 8 minutes, actually. So we sped it up quite a bit. But you can see there, effectively, we've just made this thing deliver medicine to our imaginary patient with no actual remote control. So once we were able to demonstrate that and be confident that we could make it a repeatable process, we actually coordinated with ICS CERT. I think some folks there in Idaho might have actually helped coordinate this, along with the FDA to communicate this to the manufacturer. And what the result was, around June last year, they actually issued a voluntary recall of all of these MiniMed 508 devices.
So the primary reason for the recall, beyond the obvious patient safety risks, is that that pump is not programmable or updatable. There's no mechanism to update the firmware. The device is locked as manufactured. And additionally, the recall affected multiple versions because in addition to the 508 pump that we were experimenting with, that transmitter receiver pair or circuitry was used across a number of models. You can see here the 508 in addition to a number of MiniMed Paradigm models as well.
Not to play down the patient safety risks either. Anytime that you can have some type of cyber effect that leads to physical harm or patient harm, that's not good, right? And especially for diabetics, hypoglycemia, so too much insulin, or hyperglycemia, not enough insulin, obviously not good conditions to be in, especially if they're a result of somebody else attempting to deliver or deny delivery of medicine.
So there were a number of recommended mitigations, and you can see the list here, but I want to highlight 3 of them specifically. The first one is don't share the serial number. That's tantamount to sharing your password. Of course, that doesn't stop somebody from capturing that password by listening for stray RF. But it is a mitigation. The second is don't disable the alarm on the infusion pump. Normally, when you're interacting with it, there's an audible alarm that you can hear that tells you when a dosage is being set, when delivery is started, or when delivery has stopped. But you can deactivate that audible alert if you want to. And if you do that, the only warning that you're going to have that delivery has started or stopped is by hearing the physical pump inside the infusion pump. And the third and most important mitigation is if you can support it, the device does not have to be used in RF mode. You can deactivate RF entirely, or you change the serial number in there, but more importantly, you can turn off RF. Again, there are use cases where RF is definitely a plus, especially with small children. But if it can be supported, the device should not be used with RF turned on. And with that, that concludes our talk today. Again, thank you for having us, and we'll open the floor for questions.
I know we had some audio problems there, so there were not a lot of questions that we had as we went. I want to give everybody in the chat a chance to ask anything if they have anything. The only one question that we did get is, will the slides be available? So at some point, we'll definitely want to talk about that.
Yeah, sure.
We have a couple of people who are typing, so we'll give them just a moment.
Hopefully at least partially hearable.
It was just kind of hit or miss. The one question that we do have here is, how concerned are you about this kind of thing being exploited either now or in the future? So I'm guessing, I'm just reading between the lines, it sounds like, have you seen this in the wild, or do you expect to see this in the wild?
Yeah, I mean, I think the big thing, the reason why the FDA stepped in is they're absolutely concerned, even if the likelihood that somebody's just going to walk by you and shoot some stray RF at you that'll activate your insulin pump, that's probably low. But the fact that it's possible is risk enough, especially
Right.
wasn't able to be patched or updated. So that piece, the recall is nice because they can no longer be prescribed to patients, this particular series of pumps, but you can still buy them on medical sites like MedWow that sell used medical devices. So they're still out there, available for purchase if folks want to use them for some reason.
And maybe we're not going to see this much as an exploit for nefarious purposes, but certainly the simplicity of the device makes it desirable to the homebrew community, right? People have built their own rigs for personal glucose monitoring using home-built apps, and their own interactions with their infusion pump. I'm sure people got different feelings on this. The FDA is going to say that that's a risk because you're using the device in an unintended manner, and it may have unintended consequences. That to each person to decide on their own. Their thoughts on
Okay. Guys, I think that's pretty much it for our time. So thanks very much for your time. And if you want to, if you have those slides shared at some point, drop into the Track One chat and toss that in there for us as well.
Yeah,
Thanks, guys.